Hello students and welcome to Chemistry A. I'm Ms. Slate and today we're going to be talking about valence shell electron pair repulsion model, also known as VSEPR, and we're also going to be talking about polarity. So valence shell electron pair repulsion model, also known as VSEPR, sometimes called VSEPR model, is a way for us to predict the shapes of molecules based on how many shared and unshared pairs of electrons those particular molecules have. Electrons that surround the central atom of a molecule are going to repel each other because all electrons are negative and like charges repel each other. Unshared electron pairs, however, occupy a slightly larger area than the shared electron pairs do. And because of that, they will often bend the molecule into different shapes. So here is a copy of the VSEPR chart, and you will be receiving one of these charts as well. So on the left, it tells you how many total pairs of electrons there are in the molecule. The next column is related to how many pairs are shared in bonds, and then the third one is unshared. And based on how many total pairs and how many shared and unshared pairs, it fits into one of the various shapes, being linear, bent, trigonal planar, pyramidal, or tetrahedral. And again, when we're looking at the total pairs and the number of shared and unshared pairs, this is based on the central atom, okay? So we're always looking at the central atom when determining how many shared and unshared pairs of electrons there are. Additionally, double and triple bonds only count as one pair of shared electrons, okay? So even if it's a double or a triple bond, that still counts as just one pair shared for the purposes of VSEPR. Let's look at a couple of examples of using VSEPR. So our first one is boron trifluoride. So the first thing I'm going to do is I'm going to make the Lewis structure for boron trifluoride so that I can determine how many shared and unshared pairs of electrons it has. So boron has 3 valence electrons. And remember, boron is an exception to the octet rule, so it only needs 6 valence electrons to be happy and stable. So it's going to share 1 electron, which each of the fluorine, of which there are 3. And fluorine only needs 1 more valence electron for it to have a full octet. So now everything has a full octet, it's all satisfied. Again, we could also just rewrite this like so for the Lewis structure. Now remember, for the purposes of VSEPR, I'm only paying attention to the shared and unshared pairs on boron. So boron has 1, 2, 3 shared pairs. Of electrons, and it has 0 unshared pairs. So now we look at our VSEPR chart. So the total number of bonds is 3, and unshared pairs is 0. So we're looking at a trigonal planar shaped molecule. So that's how I know boron trifluoride is trigonal planar. Our second example is sulfur trioxide. So sulfur has 6 valence electrons, and so does oxygen. So what that means is that one of the oxygens is going to need to have a double bond with sulfur. And the other 2 will have a single bond. with sulfur. And you can see this way, now everything has 8 electrons, so all of the atoms have a full octet now. So again, for the sake of VSEPR, again, we're looking at the central atom. It's got 1, 2, 3 shared pairs of electrons. Because remember, the double bond is still only counting as 1 for the purpose of VSEPR. And just like boron trifluoride, it's got 0 unshared pairs, which means it's going to have the exact same shape of being trigonal planar. And you'll be able to use the VSEPR chart here on your test as well as the final exam. So I'm not going to make you memorize any of the VSEPR stuff. This is just another thing you're going to be able to use, just like your periodic table. Now that we've talked about VSEPR and molecular shape, let's talk about bond and molecule polarity. So first up, a brief review of bonding, right? We know for ionic bonding, something like sodium, a metal, wants to lose an electron because it has just 1 valence electron, while something like chlorine wants to gain an electron because it has 7 valence electrons. Again, remembering the octet rule, everything wants to have 8 valence electrons because that's its most stable arrangement, with a few exceptions. So in the case of sodium and chloride, an electron will be completely transferred from sodium to the chloride ion. Again, because sodium wants to lose its electron, chloride wants to gain its electron. As a review, this ability of an atom to attract electrons in a chemical bond is called electronegativity. We talked about this in our previous unit. And these values increase within a period as atomic number increases. And we use electronegativity to help us evaluate the polarity of a bond. Basically, how much has one atom attracted the electrons in the bond over the others? So, for example, fluorine is the most electronegative element. It has an electronegativity of 3.98. Francium is the least electronegative element. It's got an electronegativity of 0.7. And these electronegativities are given on a chart of the periodic table that should be on the back of your VSEPR chart. Again, because francium has a very low electronegativity, it's not going to really attract electrons at all. Because fluorine has a very high electronegativity, it's going to very strongly attract electrons to it. And again, how much one atom over the other attracts most of the electrons in the bond is what determines polarity. So again, more simply, we're going to be looking at the difference in electronegativity values between the two bonded atoms. And depending on how big that difference is, tells us kind of what slot or what category for bond polarity that particular bond falls into. So if the difference in electronegativity between the two atoms is between 0 and 0.4, we say the bond is nonpolar covalent. If the difference is between 0.4 and 1.7, we'd say the bond is polar covalent. And lastly, if the difference is greater than 1.7, we say the bond is just predominantly ionic. So what do all these terms mean? If we say something is nonpolar, what we mean essentially is that the two atoms in the bond share the electrons between them equally. So there's no one atom hogging all the electrons over the other. Nonpolar is an even sharing of electrons. A polar covalent bond, on the other hand, has one atom attracting most of the electrons in the bond. So because of that unequal sharing of electrons, you're going to end up with one part of a polar bond having a slightly positive charge and the other end of a polar bond having a slightly negative charge. Again, because the electrons aren't shared equally, one of the atoms in the bond is kind of hogging most of the electrons. Lastly, in an ionic bond, as we talked about before, there's a complete transfer of electrons, okay? One atom has completely lost electrons, the other atom has entirely gained electrons. So we have two completely oppositely charged ions in an ionic bond. Now, that was bond polarity, okay? So when we compare electronegativities, we're looking at, is the bond between two specific atoms polar, nonpolar, or ionic? We also talk about molecule polarity, though, okay? Molecule polarity is determined partially by bond polarity, but also partially by the molecule's symmetry, okay? In general, if a molecule is asymmetric, the molecule is going to be polar. Because if it's asymmetric, it's probably going to have a partially negative end and a partially positive end. On the other hand, if a molecule is symmetric, the molecule is going to be nonpolar, even if all the individual atom-to-atom bonds are polar. Because if it's symmetric, that unequal sharing of the bonds is going to be evenly distributed to all the sides of the molecule. So again, the molecule overall itself will still be nonpolar if it's symmetric. Let's look at some examples, okay? Let's look at water. The electronegativity of oxygen is 3.44, and the electronegativity of hydrogen is 2.20. The difference is 1.24. So that difference tells us that it is a polar covalent bond. So the bond between hydrogen and oxygen is polar covalent. Now, if we look at the shape of the molecule, so if you were to look at your VSEPR chart, you'd be able to determine that water is, in fact, a bent molecule, right? It's got this shape. Now, the bent molecule is not symmetric, okay? We don't have bonds evenly distributed in all directions. So the water molecule is asymmetric, which means the water molecule itself is polar. So water has a partially negative end and a partially positive end. And we can actually look at that, we can actually show that partial positive and partial negative of water in a simple demonstration. So as we saw in the clip, the video clip, when I took the negatively charged balloon near the thin stream of water, the water bent towards the balloon. And again, that's because the end of the water molecule with the hydrogens has a partially positive charge, which is attracted to the negatively charged balloon. Again, because water is a polar molecule. The molecule has a slightly positive end and a slightly negative end. Let's look at another example, carbon tetrachloride. Chlorine has an electronegativity of 3.16. Carbon is 2.55. The difference is 0.16, which means we've got a polar covalent bond. So each individual carbon-chlorine bond is polar. However, the shape of carbon tetrachloride is a tetrahedral, okay? So the tetrahedral molecule shape has bonds going off in all directions evenly. So this molecule is in fact symmetric, which means that even though each individual carbon-chlorine bond is polar, because those bonds are distributed in an even way, the molecule itself is nonpolar. Again, the individual bonds can be polar, but if the molecule is symmetric, it will be a nonpolar molecule. Hydrogen gas is another example. Hydrogen has an electronegativity of 2.2. That means our difference is 0, which means the bond polarity is non-polar covalent. So the electrons between the two hydrogen atoms are shared equally. The shape of a hydrogen molecule is linear, right? So it's just in a line. We've got bonds evenly going in both directions, which means that the linear molecule is symmetric. So again, we have a non-polar molecule. So nonpolar covalent bonds and a nonpolar molecule because a linear molecule is symmetric. Ammonia, NH3. Nitrogen has an electronegativity of 3.04. Hydrogen is 2.2. The difference between them is 0.84. Again, that indicates a polar covalent bond. So each nitrogen-hydrogen bond is polar covalent. According to VSEPR, ammonia has a pyramidal molecular shape. Again, look at the pyramidal shape. We can see that the bonds aren't distributed evenly in all directions. So that means this is an asymmetric molecule. Again, asymmetric molecules are going to have a molecule polarity that is polar. So this is an example where we had polar covalent bonds and a polar molecule because it was an asymmetric shape. So let's talk about some of the importance for polar and nonpolar bonds. First off, a lot of properties of compounds can be determined by the bond type between the atoms. So for example, polar substances will dissolve polar and ionic substances, okay? But nonpolar substances will only dissolve other nonpolar substances, okay? Typically, when we're trying to remember this, we say like dissolves like. So this is why something like water can dissolve pretty much all ionic salts because it's polar. Polar substances dissolve other polar substances and ionic substances. But something like styrofoam doesn't dissolve in water because styrofoam is a nonpolar molecule. And that wraps up our discussion of VSEPR and molecular polarity.